Hello once again, calculus students. The topic for today is the derivatives of the trigonometric functions. So far we've talked about so-called algebraic functions. Examples include polynomials and rational functions, and maybe even those functions that involve square roots and cube roots and so on. Algebraic functions are those functions that are defined in terms of elementary arithmetic operations, addition, subtraction, multiplication, and division, and of course extracting roots. But you're aware of other kinds of functions, in particular the trigonometric functions, that are not defined in terms of those basic arithmetic operations. This makes developing their derivatives a little bit trickier, and that's one of the objects of today's lesson, is to develop derivative rules for the trigonometric functions. And then, after we've developed those rules for differentiating trigonometric functions, we'll of course practice plenty of examples.
Hello once again. Today's topic is derivatives of trigonometric functions. Now, before we can just jump in and start calculating derivatives of trigonometric functions, we actually have to establish a couple of preliminary limits. These, what I like to call the fundamental trigonometric limits, which are these limits in theorem 3.10. The limit as x approaches 0 of sine of x divided by x turns out to be equal to 1. And the limit as x approaches 0 of cosine of x minus 1 all divided by x comes out to 0. Of course, both of these limits here, you can't simply do direct substitution because you get division by 0. But you may notice that both of those limits, if you try to plug in 0, you get 0 in the numerator and the denominator. And those are the kind of limits where we have some hope that we can get it to work out. It turns out, though, that for these limits, there's no amount of sophisticated algebra or applying trigonometric identities that you can do to show that these identities work. You really have to look at a geometric figure to establish some inequalities and then use the squeeze law to verify these. So that's going to be our game plan for seeing why these two limits are true. So, like I said, the idea, we're going to take this figure at right over here, figure 1, that involves some triangles and how they meet with a semicircle, and we're going to use what we know about the geometry of that situation to establish an inequality that involves the thing that we're interested in, sine of x over x, to start with, and then we'll apply the squeeze law. So this will be our strategy. So put your eyes on figure 1 for a moment. There are 3 geometric things that are related to one another there that I want to draw your attention to. The first one is the triangle OAC. So let me shade that here in red. That'd be like this triangle here. Now, that triangle sits inside of what's called a circular sector. It sits inside this circular sector like that goes here in yellow. And then that yellow circular sector in turn sits inside this triangle OBD, which maybe I can shade that in blue out here, like this. So because the red triangle sits inside the yellow area and the yellow area sits inside the blue area, I get that inequality in blue right here. So that inequality is just an observation that, these 3 figures are, one inside the next. And so the areas satisfy that inequality. So what I want to do is next work out what those areas are. So let's start with the red triangle, the smallest one. In this figure, the circle is radius 1, centered at the origin. So it's a unit circle, right? And the angle of that line OB, the angle that it makes with the positive x-axis, is what we're calling the angle x. And so that means that the coordinates at the point A are cosine x, comma sine x, because that point A is just the point on the unit circle at the angle of x. So that means that the horizontal side of that smaller triangle, OC, is cosine of x, and then the vertical side would be sine of x. So that line segment AC has length sine of x. And that's a right triangle. Maybe I didn't depict it there in the figure, but yeah, these are right angles here and here. So that first area, when you have a triangle, it's 1/2 the base times the height, right? So this area would be 1/2 the base is cosine of x, and the height is sine of x. So I'm using that area formula for a triangle, 1/2 base times height. In the yellow region, the circular sector, OAD, in figure 2, I have a formula there that tells you how to find the area of a circular sector. If you know the angle of the circular sector, you know the angle of the red piece of pie there, the area turns out to be 1/2 the radius squared times the angle theta. And of course, we're assuming that all of our angles are measured in radians here. If we were trying to measure angles in degrees, our formulas would be a little bit off. So it's important that all our angles are in radians. In any event, that's your formula for a circular sector. So if you apply that to the yellow region, your radius is equal to 1, and your angle theta is x. So in the middle, for that area of the circular sector, you get 1/2, and then r squared, so 1 squared, and then the angle is x. And then the triangle OBD, the one that we shaded blue, well, we need to know, we want to do again, the area of a triangle is 1/2 the base times the height. I can see that the base is 1 because the base of that triangle goes from 0 to D, and D is at the point 1 on the x-axis. So I need to figure out what the height of this triangle is. Let me call it y. So BD I'm going to call y. And let me find a little place to just do a little scratch work here. Notice that in triangle OBD, so I'm writing up here in the upper right-hand part of the page. In triangle OBD, if I look at tangent of x, remember that's the opposite over the adjacent in a right triangle. So tangent of x is the opposite, which we have labeled y, and the adjacent is the bottom side of that triangle has length 1. So the moral of the story from that little calculation there is that y is equal to tangent of x, it turns out. So that's the height of that triangle OBD. So now that I know the base and I know the height, I can calculate the area of it. It's 1/2. The base is 1, and the height is tangent of x. Okay. Now I need to play around with this inequality a little bit. I want to get sine of x divided by x. Well, one thing I'm going to do right off the bat is multiply through the whole inequality by 2 to get rid of those 1/2s. But I'm also going to divide everything by sine of x. So if I multiply by 2 and divide by sine of x, I'm going to end up with cosine of x less than or equal to x over sine of x less than or equal to, the 1/2 went away. Now, if you do tangent, let me go to the side here somewhere. Tangent of x over sine of x, I'm dividing through by sine. Well, tangent of x is sine of x over cosine of x. So what I'm really doing there is multiplying 1 over sine of x times sine of x over cosine of x. And so those sines cancel off, and you're left with 1 over cosine. So that's what happens on the right-hand side of that inequality. You just end up with 1 over cosine of x. So here well, let's just say it this way. I multiply everything by 2 over sine of x. And I can get away with that because I'm assuming here that my angle x is between 0 and pi over 2. And when x is between 0 and pi over 2, I know sine is positive. And so what I'm doing is I multiplied through that inequality by a positive number. And so it doesn't change the inequality. Okay. Now look in the middle. I've got x over sine of x. So I want to reciprocate that. It turns out if you reciprocate both sides of an inequality, it just has the effect of reversing the inequality. So if I reciprocate this first inequality here, it'll become 1 over cosine of x is greater than or equal to sine of x over x. And likewise, when I reciprocate the second inequality, it becomes sine of x over x is greater than or equal to cosine of x. I'm going to just go ahead and write that inequality where the inequalities are pointing the other way. So just turn the whole thing around like this. Okay, so now we're at the point where we can apply the squeeze law. Remember, we have this basic limit that limit as x goes to 0 of cosine of x is equal to 1. So because of that basic limit, I can calculate the limits in this inequality here, the extremes of it. So cosine of x goes to 1 as x goes to 0. And likewise, 1 over cosine of x, I could just apply the the quotient limit law, and I'd take the limit of the top over the limit of the bottom, and I would still get 1 as x goes to 0. So by the squeeze law, I get that sine of x over x goes to 1. Well, I have neglected something here, actually. I guess all I've really shown is that the limit as x goes to 0 on the right of sine of x over x equals 1. But actually, I can get the two-sided limit pretty easily. So my next little trick to get the two-sided limit would just be to point out that if you look at the left-hand side of 0, for x's on the left-hand side of 0, you'd have, let's look at those x's between negative pi over 2 and 0. So negative values of x. For those values of x, if I negated the whole thing, I would have 0 is less than negative x is less than positive pi over 2. And since we've already established this inequality right here in green, that inequality has been established for values of x between 0 and pi over 2, then I can get away with saying cosine of negative x is less than or equal to sine of negative x over negative x is less than or equal to 1 over cosine of negative x. But we have some identities that say things like sine of negative x is equal to negative sine of x. And we know that cosine of negative x is just equal to cosine of x. So that tells me that I still have that same inequality, cosine of x less than or equal to, well, that middle inequality, you get negative sine of x over negative x, but then those negatives cancel, right? So I can just get rid of them. So the point is that the inequality that we did in green also works whenever x is negative. So that means when I did my squeeze law bit, I didn't have to think of it as a one-sided limit. I could have done a two-sided limit because the inequality is true on both sides of 0. So this tells me by the squeeze law, the limit as x approaches 0 on either side of sine of x over x is equal to 1. Okay, so we've established that one. And once you know that one, you can actually use the limit of sine of x over x to get the second limit that we wanted to argue. The second limit was the cosine of x minus 1 over x limit. So let's see how we get that limit. Actually, I can just get it by doing a little bit of algebra, using some trigonometric identities, and actually you can get it pretty quick. So what I'm going to do is multiply by a sneaky sort of conjugate. So I'm really just multiplying by 1 here, but what effect does that have on that limit in black? When you multiply it out in the numerator, you end up getting cosine squared of x minus 1, and then you have x times cosine of x plus 1 in the denominator. Now up here in the upper right hand corner, I'm going to remind you that Pythagorean identity is sine squared of x plus cosine squared of x equals 1. So by manipulating that equation, cosine squared of x minus 1 would be equal to negative sine squared of x. So I'm going to make that substitution. Negative sine squared of x in the numerator. Then I've got this x times cosine x plus 1. And at this point, I'm going to just break things up a little bit so that I can take advantage of the other limit that we already proved, that limit as x goes to 0 of sine of x over x is equal to 1. So I can take that big fraction there and break it up like this. I can do a sine of x over x, and then I have times, I could have a negative sine of x divided by cosine of x plus 1. And this limit we can evaluate right away, because what do we know that sine of x over x goes to as x goes to 0? Well, that's what we just verified a minute ago. That's 0. I'm sorry, oops, that goes to 1. And then the second expression there, we can evaluate by direct substitution, because direct substitution does not result in 0 in the denominator. It results in 2 in the denominator. You get, when you do direct substitution there, you get negative, and then sine of 0 is 0 over 1 plus 1. So that just equals 0. Evaluating that limit comes out to 1 times 0, which is 0. And that's what we wanted to show. I guess I should have said I wanted to verify that that limit equals 0 at the beginning there. But yeah, so there you have it. So now we have both of our fundamental trigonometric limits. We can use what we just found out along with some other bits of information we already knew. In particular, these 4 limits that I'm shading in yellow here. We already knew that the limit as x approaches 0, sine of x is equal to 0, and we already knew that the limit as x approaches 0, cosine of x is equal to 1. So basically direct substitution. And then we just learned these next 2 limits. The limit as x goes to 0 of sine x over x equals 1, and then this last one. So let's see if we can put some of this together to calculate limits involving trig functions. Okay, so for that first example, sine of 3x over 2x. It looks similar to the sine of x over x limit, so the idea is we just need to manipulate it and sort of massage it until it looks exactly like that limit of sine of x over x as x goes to 0. So here's what we can do. Let's let t be 3x. And then if t is, so I'm wanting to make a substitution so that the argument of the sine function is just a single variable, like it is in our limit in yellow at the top there on the left. So I want to convert that 3x to just a single variable t. But if I do that, I want to observe 2 things. One, x would be equal to t over 3, and 2, as x goes to 0, so does t. T would go to 0 because t is just 3 times x. And so 3 times something that's very small is also very small. So with those observations in place, I can write this next thing as the limit as t goes to 0. And then instead of sine of 3x, I've got sine of t. And then I've got that 2. And then in place of x, I can put t over 3. But that's the same as the limit as t goes to 0 of, well, in the denominator there, I've actually got 2/3. So that's the same as 3/2 out front multiplied times sine of t over t. And then I'm going to just pull that 3/2 out of the limit. And what I'm looking at this point is the limit as t goes to 0 of sine of t over t. And that's identical to the limit in yellow at the top left, with the exception that, we're using the variable t instead of x. But we know that that limit's equal to 1, so we just get 3/2 times 1, or 3/2 for our final answer. Okay, here's another example of a trigonometric limit. What's jumping out at me is that, we have the Pythagorean identity, sine squared of theta plus cosine squared of theta equals 1. And so I can rewrite that as cosine squared of theta minus 1 equals negative sine squared of theta. So I think I'll try to use that. Like so. I think what we need to do next is tease apart that sine squared. So I want to utilize that sine of theta over theta limit. So I could write this as sine of theta over theta multiplied times negative sine of theta. And that's cool, because now I see that this breaks up as 2 limits that I can evaluate. I can write this as limit of sine of theta over theta times the limit as theta goes to 0 of negative sine of theta. And that first limit's equal to 1. And that second limit's equal to, you could pull the negative out and you'd be taking the limit of sine of theta as theta goes to 0, and that gives you 0. So you get 1 for the final answer. I'm sorry, oops. 0 times 1 is actually 0. So 0 is the final answer. So yeah, we can evaluate a wider variety of trigonometric limits now that we have these fundamental trigonometric identities. And more importantly, possibly, is that we can now calculate the derivatives of the sine and cosine functions. Here are some basic facts that you're going to need to know. I guess probably never get to forget it during the rest of your career as a calculus student. The derivative of the sine function is the cosine function. And the derivative of the cosine function is negative the sine function. And so now that we have our trigonometric limits in place, we can actually verify these derivatives. So let's do that for the sine function. We'll do it for the cosine function too. So if I want to take the derivative of the sine function, I don't have any other information at this point other than to use the definition of derivative. So that's what I'll do. So the definition of derivative for this function would be limit as h goes to 0, sine of x plus h minus sine of x, all divided by h. And then next, I'm going to use this identity that says sine of x plus h would actually be equal to sine x cosine h plus cosine x sine h. So that's called the sum of angles identity. So if I apply that here, I'll have the following. So in this step that I just did here, I just replaced sine of x plus h with, what it's equal to in the sum of angles identity. And now we want to set this thing up so that we can take advantage of those fundamental trigonometric limits that we know. Well, if I take let me circle some things here. If I take the first term in the numerator and combine it with the third term in the numerator, I would get something like this. Sine x cosine h minus sine x over h times, and then I'm going to have the second fraction, plus cosine x sine h over h. And to make things look just a little bit clearer, I'll write this as limit as h goes to 0. I'm going to pull that sine of x out to the front. See, in that numerator of that first fraction, I can factor the sine x out in the numerator, and then I can just set it to the front of the fraction cosine h minus 1 over h, plus, on that second fraction, I'll pull the cosine of x to the front and just have the fraction sine of h over h. And I can look at each of these little pieces. Sine of x. Now, it's important to notice that it's h that's going to 0 here. Sine of x doesn't have an h in it. So as far as it's concerned, it could care less that h is going to 0. So there you just get sine of x. And then this next fraction is one of those fundamental trigonometric limits that we were talking about at the beginning. And it turns out that that goes to 0. And then cosine of x, again, it doesn't have an h in it. So you just get cosine of x when you take the limit as h goes to 0. And then this last little fraction here, sine of h over h, as h goes to 0, that's another one of those fundamental trigonometric limits, and it comes out to 1. So you can see what this works out to. Sine times 0 is 0, plus cosine times 1 comes out to cosine of x. And that's what we're expecting, right? We showed that the derivative of sine equals cosine. It's a pretty similar computation to prove that the derivative of cosine is negative sine. Let's do it. It would be a good idea for you, just to make sure you're understanding things, to press pause here and see if you can get the answer yourself. All right, so I'm going to set this up as taking the limit as h goes to 0, cosine x plus h minus cosine x, all divided by h. Next, I'm going to apply what's called the sum of angles identity for cosine. So there's an identity that I can use to replace this cosine of x plus h with something that kind of expands it. And that identity looks like this. It's going to be cosine x cosine h minus sine x sine h. Then I still got that minus cosine x that was already there, all over h. So what I have in blue there is the sum of angles identity for cosine. And that's what I applied for that step. And then, just like before, I'm going to group the first term and the third term in the numerator together, the terms that have the cosine of x on them. And I can pull that cosine of x off of them, and I'll end up with cosine h minus 1 over h. And then I'll have a minus, because of the minus in the middle term in the numerator. And I'm going to pull the sine of x off to the front, and then it's going to be multiplied times sine of h over h. And then when you examine each of the pieces like we did before, the terms that don't have an h in them just stay themselves. So cosine of x and sine of x just stay cosine of x and sine of x. Cosine of h minus 1 over h goes to 0. That's one of our fundamental trig limits. And then that last fraction there goes to 1. And you can see what you end up with. You got cosine times 0 minus sine times 1. So just minus sine x, which was what we were expecting to get. All right. So now you know why the derivative of sine is cosine and the derivative of cosine is negative sine. It was very heavily dependent on those two fundamental trigonometric limits. We used it both times. So you can see why we needed those limits. But now we've got these things established that derivative of sine is cosine and derivative of cosine is negative sine. So we can use those two facts to establish all the other 4 trig functions, right? Because everything can be written in terms of sine and cosine. Tangent is sine over cosine. So if I want to differentiate the tangent function, I can just differentiate sine over cosine and use the quotient rule. Similarly, cotangent of x is cosine of x over sine of x. So again, to get the derivative of cotangent, I could use the quotient rule and what I know about sine and cosine. Secant is 1 over cosine. Again, you can use the quotient rule. And cosecant is 1 over sine. So again, we can use the quotient rule and what we know about sine and cosine to get all of the other ones. So for example, what is the derivative of tangent? Well, it's the same as doing the derivative of sine of x over cosine of x. And then I can use the quotient rule. So that would be, okay, you multiply times the denominator times the derivative of the numerator. Then you do a minus. Then you leave the numerator alone and multiply times the derivative of the denominator. And then you divide by the denominator squared, which we write as cosine squared of x like that. And we just learned that the derivative of sine is cosine. So in that numerator, we get cosine x times cosine x minus, then we have sine x, and the derivative of cosine is negative sine. So what we really have in the numerator there is cosine squared of x plus sine squared of x all over cosine squared of x. And we remember the Pythagorean identity says the numerator is equal to 1. So that's 1 over cosine squared of x. And because the reciprocal of cosine is what we call secant, we can just call this secant squared of x. And that's the derivative formula for tangent. Derivative of tangent, the standard way to write it is just secant squared of x. And you can do that for all of the trig functions, and the results are summarized here in this table. You can see the one we just did here. Agrees with my answer, right? Yep. So all of them are fairly easy to, derive from the knowledge that derivative of sine is cosine and the derivative of cosine is negative sine. So these are 6 derivatives that you need to know. You need to know all of them by heart. Let's do this example here of calculating a derivative. So I've got y equals this fraction, sine x plus cosine x over e to the x. If I'd like to calculate the derivative, well, I could do the quotient rule here. That would be, remember you take the denominator and then you multiply times the derivative of the numerator. Then you do minus. Then you take the numerator, left alone, and you multiply times the derivative of the denominator. And then you divide that all by the denominator squared. So for this particular example, I'd end up with e to the x. And then the derivative of sine plus cosine would be cosine of x minus sine of x. Then I have minus sine of x plus cosine of x. And then the derivative of e to the x is just e to the x. And then you have e to the 2x in the denominator. And I could do a fair amount of simplification on this. Like I could factor an e to the x out of the top and just end up with, and I also see that after I did that, I could cancel the cosines off because there's a negative cosine and a positive cosine. So looks like you're going to end up with negative 2 sine x over e to the x is what that all collapses down to. Check me and make sure I'm right on that. But what I did was I factored e to the x out in the numerator and canceled it with one of the e to the x's that's in the denominator. So the e to the x in the numerator went away. And then after that, I saw that there's a cosine and a negative cosine, so those go away. And then I had 2 negative signs. So I think that's right. Let's see a couple more examples of computing these derivatives involving trig functions. So for this example, I want to calculate dy dx. I can think of a couple of ways to do this, but in its current form, secant times tangent, I could just do the product rule. The product rule would say take the derivative of the first function, so that's secant, and then multiply times the second function left alone, plus, then you leave the first function alone, and multiply times the derivative of the second function. By the way, the variable there was theta, so I should be talking about dy d theta. Okay, so now I've got the derivative going. I got to remember what these derivatives are. So what's the derivative of a secant? Well, I've got this one memorized like a good boy, and it turns out to be secant theta. Tangent theta is that derivative, and then I got that multiplied times tangent of theta plus secant theta. And then we just discovered that the derivative of tangent theta is secant squared of theta. I could write this as, I think I could do some interesting simplification here if I were so inclined. I could factor out a secant, and then I'd have tangent squared theta plus secant squared theta. I can't reduce that in an extreme amount. I do know there's an identity that says tangent squared of theta is the same as 1 plus secant squared. So I could convert that to some secants if I wanted to, but I don't see any need to at this point. So I'll just leave it like that. Okay. How about if I want to take the derivative of sine squared? You see a lot of sine squareds and cosine squareds and trig functions squared as a result of the Pythagorean identities. How would I take the derivative of sine squared? I don't have a rule that tells me how to take the derivative of a whole function squared, but we can view that as sine of x times sine of x, right? That's what sine squared means. So then to take the derivative of this, I could just use the product rule. And then I'd take the derivative of the first term, then multiply times the second term left alone, plus then leave the first term alone, multiply times the derivative of the second term. So I'm going to get cosine x sine x plus sine x cosine x. But those are really the same term because when you multiply, it doesn't make any difference what order you multiply in. So I could just write that as 2 times sine x times cosine x because it's the same thing repeated twice, right? Okay, that's where we're at. We now know how to differentiate trig functions, any one of them, or products of them, quotients of them, whatever. I would advise you, as you move forward, to start taking a little look at trigonometric identities and making sure that you know the basics. I think at this point in the video, I'm going to put a link to a review sheet for trigonometric facts and identities that you may want to maybe even print it out and keep it handy for when you're doing problems, or maybe keep it on your computer. All right, we'll stop there and we'll see you again soon. Bye now.